We're on the back page of your flip book, and we're going to be doing the right column of this, just going through a couple example problems here that deal with similarity or proportionality or ratios. Here's our first question. John shoots 150 times in an entire basketball season. He makes 25 of those shots. So what is the ratio of made shots to total shots? So what you guys want to see is when it says what is the ratio of this description made shots, that goes on the first part of our ratio, or the top of the fraction. And then this word to tells us that the next part is going to go on the bottom of our fraction, or the second part of our ratio. So when you see, remember how we can say a ratio is 1 to 2? That's just 1 over 2, 1 to 2. Made shots to missed shots. So let's figure out, well, how many shots did he make? He made 25 shots. Now let's write this real quick. So really what we're thinking here is that we're going to look for made shots, and that's going to be a ratio compared to the total shots. So now let's work this out. This actually equals, class, this equals made shots. Remember, the first word goes on top, and then the word to, that means that the bottom of it is going to be total. So made to total is made to total, or made to total. You can see they all are set up the way we learned how to write ratios. And now let's go ahead and plug in our numbers. Well, made shots are 25 over total shots, which is 150. Now I can look at this and see that 25 is divisible by 5, so I can say 25 divided by 5 is 5. 150 divided by 5, I'm going to check that to make sure we're okay with that. 150 divided by 5 is equal to 30. Looks like I can reduce that again. 5 divided by 5 is 1. 30 divided by 5 is 6. So now you can see that his ratio of made shots to mixed shots is 1 over 6, and that is the same as 1 to 6. So there is our ratio of made shots to total shots. Alright, so just getting you used to the words, how the words describe the actual ratio and how it's set up. Let's take a look at the next one. James made 72 free throws out of 84. Trevor made the same ratio of free throws as James. So if Trevor made 60 free throws, how many did he shoot? Now I wrote this out. You can kind of draw these boxes. In these kind of problems, these proportion problems, sometimes it's nice to organize these. I'm going to show you how this works. I'm going to go ahead and write, let's say that we're going to put information from James in this column, and we're going to put information from Trevor in this column. And then let's organize our work this way. We're going to go ahead and put the number of the made shots on the top of our ratio, and we're going to put the total shots on this part. Now when you organize this to get this question right, all I'm doing is making sure that I keep my ratios the right way, that I don't flip them over. When you label things like this, you'll never go wrong with setting up your proportion. Let's fill out our information now. How many did James make? He made 72. How many total free throws did James shoot? He made 84. Sorry, he shot 84. Now Trevor, what do we know about Trevor? Trevor made 60 free throws. Okay, so there's our 60. And the question is, how many did he shoot? There's our variable. And watch how great this works. I'm going to go ahead and put an equal sign right here. And I'm going to make this a ratio, and I'm going to make this a ratio, and there's my proportion. And now I can cross multiply. So I'm going to go ahead and say, all right, 72 times x is 72x. And then we're going to have 84 times 60. Doesn't matter whether I write 60 times 84. It doesn't matter whether I put 72x on the other side of the equal sign. It makes no difference. Just cross multiply. Connect these two numbers together by multiplication and these two numbers together by multiplication. All right, let's do the math here. 84 times 60 is 5,040. Of course, I use a calculator to get that, so you know I can't do that in my head. Now I'm going to divide both sides by 72. If we show our Algebra 1 steps, then we know that 72 and 72 cancel, and we end up with x is equal to, let's do this one in the calculator, 5,040 divided by 72 equals, oh, exactly 70. So x is equal to 70. Well, what is x? X is the number of shots Trevor took. So our answer here should be in a sentence. Trevor shot 70 free throws. So here we're able to use proportionality and ratios to figure out the missing number of free throws that Trevor shot. And that makes his ratio of shots made to missed exactly the same as James's. All right, let's take a look at the next one. A real train engine is 60 feet long and 15 feet tall. A toy model of the train engine, a model meaning we're going to make it smaller. A toy model of the train engine is 18 inches long. If the toy model and the real engine are similar, and that means they grow, or in this case shrink, by the same proportions, how tall is the toy train? How tall is the toy train? Again, let's set this up with a table. It's going to make it a lot easier to solve our problem. So let's say I'm going to put the train information here. It makes no difference. I'm going to put the train information here. That means I'm going to put the toy information here. And I'm going to put how long they are in the top box and how tall they are in the bottom box. Now you could have rearranged this any way you want. You could have put toy and train here and long and tall here. You could have flipped around the toy and the train. You could have flipped around the long and the tall. It makes no difference. But now the key is you're going to follow along with your information and plug things into the right boxes. The real train is 60 feet long. And I'm going to put the unit of measure here just to show you what happens. 60 feet long. And the real train engine is 15 feet tall. All right? And then the toy model, all we know is how long it is. It is 18 inches. We don't know how tall it is. We're looking for how tall is the toy. So this is going to be our x. Let's go ahead and change this into a proportion. This is going to be your divider. There's your fraction divider. We're going to put an equal sign right here. Now what I want you guys to see is that the feet cancel. We've got feet on top and bottom, so that can actually be crossed off. But the inches can't be crossed off because we don't have another unit of measure in our proportion that has inches. At least not one that's on the bottom, so we can't cancel. You can only cancel if you're looking at top to bottom. So that gets rid of our feet measurement. That works out pretty good. And let's multiply this out. X times 60 is 60x. That's equal to 15 times 18, and we still have inches on the 18. All right, that means 60x is equal to 15 times 18 is 270, and we still have those inches hanging around. And now we're going to divide both sides by 60. This leaves x by itself. Let's do 270 divided by 60. 270 divided by 60. And now we figure out that x is equal to 4.5, and we still have inches. We've never been able to cancel that. That tells you that the toy train is 4.5 inches tall. So the toy train is 4.5 inches tall. So I want you guys to see how nice it is when you're dealing with proportion problems or proportion word problems. If you set it up like a table like we have here with 2 columns and 2 rows, have room for your descriptions, put your descriptions in there, whatever you're told in the picture or in the story, and then just use those headings and columns to go ahead, or columns and rows to go ahead and fill out your information, create it as a proportion or change it to a proportion, and then solve for the missing value. Easy peasy. All right, last one. What is the scale factor? Well, you've done this already in class. If you want to figure out scale factor, you better figure out what is the pre-image and the image. In this case, the P vertex does not have prime notation. That must be the pre-image. That makes this the image, and that makes this a reduction. So I'm going to have to, for scale factor, remember scale factor is equal to a measure from the image over a measure of the pre-image. The measure from the center of dilation to the image or the copy is 8. And the measure to the pre-image is 24. We can divide top and bottom by 8. That's 1/3. And so our scale factor is 1:3. Now take a look. If we look at this fraction, it's less than 1. That tells you it is a reduction. And that makes sense. This is a reduction because the scale factor is less than 1, and our picture shows us we're reducing our shape from a bigger size to a smaller size. Let's try this one. This one again, let's determine what the pre-image and the image are. My pre-image is the one without the prime notation. That's the smaller one. That means the bigger diamond is the image. Remember our scale factor. Oh, let's go ahead and draw to here. We know that we are now making a bigger shape because the pre-image is getting bigger. Our scale factor is going to be a measurement from the image over a measurement from the pre-image. From the center of dilation, actually they don't even tell you the center of dilation measures, but they do tell you 2 corresponding sides. The side on our image, our copy, is 16. That same side on our pre-image is 6. We can divide top and bottom by 2, and we end up with 8/3. That scale factor is 8:3. And that makes sense, class. Now if you would on this one, go ahead and put an arrow here and write this is an enlargement. Let's do that in green like the other one. If the scale factor is greater than 1, that means we are enlarging the image, and that makes total sense because we're getting a small diamond is turning into a big diamond. So there's how we can figure out what the scale factors are of these 2 diagrams.